Well, hello everyone. Thanks again for joining us for another one of these podcasts. This one's live, obviously. This one's not offline. Luckily today, I'm joined by Professor Tom Stace from the University of Queensland and the Australian Research Council Centre of Excellence for Engineered Quantum Systems. So, Tom, thanks for joining us.
Oh, you're welcome. It's good to be here.
So I thought we'd start this discussion off with a much sort of a broader perspective of specifically EQuS, the centre that you work for, and the kind of work that EQuS does, and how this sort of fits in more globally with this idea of quantum technology, because EQuS is not mandated to look exclusively at quantum computing, but rather quantum technology in general. So can you give us a bit of a rundown of how that works in sort of the pie in the sky kind of look?
Sure. So quantum mechanics has been of interest to scientists for 100 years or more. And for a long time, probably the first half of the life of quantum mechanics, it's been seen something as a curiosity or as a source of noise, a source of problems. And I guess we've been realizing over the last 20 or 30 or 40 years that there are things that quantum mechanics lets you do in a positive sense that you can't do with just a classical model of the universe. And as you sort of alluded to, quantum computing is one area that's true. There are certain tasks in quantum computing that you can solve more efficiently than you can do with classical computer. But that's not the end of the story. There are a lot of other questions and problems that potentially we can solve in the world with quantum technologies that aren't digital computers in the sense of a pre-programmable gate model of computation, but that nevertheless you can exploit quantum mechanics to your advantage. So one of the sort of staple examples of that is measurement. So measurement is always affected by noise. So classically or quantum mechanically, there's always noise in measuring some object, something that you're interested in. And so metrology, which is the study of measurement, really is in a sense a study of noise. It's asking the question, how do we measure things and minimize noise? Now, quantum mechanics imposes a minimum amount of noise. There's randomness in all quantum systems, but it turns out you can use the power of quantum mechanics to circumvent some of that noise, to mitigate some of that noise. And there's a great example of where people are working very hard, and one of the first places that people have thought to deploy such a quantum measurement scheme is in LIGO, so the Large Gravitational Interferometer that recently discovered gravity waves. That system is a very powerful laser that's circulating in gigantic 4-kilometer long vacuum tubes. So it's a massive piece of machinery, but at its heart, it's measuring photons, it's measuring light. And those photons have noise associated with them because they're quantum mechanical particles. And trying to make measurements of these gigantic interferometric arms to detect gravity waves really is just a question of how low can you push noise. And that noise can come from fundamental sources like quantum mechanics. And it can also come from more prosaic things like trucks driving past, they shake the mirrors. But either which way, it's really the problem that experiment is solving is how do we engineer noise to be as small as possible. And one of the tricks that's been developed for LIGO is how you use quantum mechanical effects, that is unusual states of light that aren't just the analog of classical light sources, aren't just the analog of lasers and light globes. How can you engineer new sources of light that are really fundamentally quantum mechanical that do a lot better at measuring lengths in that case? Now, it turns out that the well-heralded LIGO experiment from a year ago or thereabouts did not, in fact, have a quantum mechanical light source implemented at the time. So we can't really claim that quantum mechanics was at the heart of that particular experimental run. However, it is the case that system is going to be upgraded with a new so-called squeezed source of light. So that's a long-winded way of saying that quantum mechanics of course, helps you to do some things in quantum computing, but it also helps to do solve real world problems and scientific problems that are really questions of noise, and how do you minimize noise in measurement. So quantum metrology is one of the areas that EQuS is really interested in. How do you use quantum mechanics, quantum mechanical principles to do measurements better and faster?
So, I mean, give us sort of a 30-second or a 45-second sort of rundown on this term, engineered quantum systems.
Sure. So again, the history of quantum mechanics has been one of physics, like out of answering questions that are of interest, scientific interest to physicists. But it's really a study of noise in one sense, and so that noise is a problem that affects all of engineering, and particularly if you think about control theory, that's really a study of how you control complicated systems that are perturbed by noise. And so engineered quantum systems is really the extension of that idea to the quantum domain. That is, how do you design apparatus that perform useful functions in the world, like measurement, that really circumvent the constraints that classical sources of classical metrology schemes really suffer from. So engineering really is a question of minimizing noise and designing things that work even in spite of real world constraints like quantum noise, quantum randomness.
So, I mean, in the context of this kind of thing, of sort of noise and sort of measurement, you've already talked a little bit about optics, about how in the case of LIGO, these kind of engineered light sources can help us out with these kind of experiments. But this kind of ties in nicely with the conversation we had a couple of weeks ago with Jake Taylor, who talked a little bit about these what are called optomechanical systems, so these quantum mechanical vibrating things. About that in the context of transducers and other kinds of devices that either sort of convert signals from one to the other, or, as you say, measure things. So this stuff is not just based on light and not just based on optics. There's a whole swath of systems that we can start looking at with this, isn't there?
Indeed, there sure is. I mean, I guess I mentioned light because that was the in many ways the starting point for people thinking about all of this sort of stuff. There's, as I just said, one sense in which you can understand the engineered in our title of engineered quantum systems is understanding sort of control theory and how noise affects engineered control systems in fighter jets and so on. There's another sense in which we use engineering in our title, and that relates to the notion of simulation. So before digital computers existed, if you wanted to solve a complicated series of differential equations, then one of the ways to do that was to build a system a mechanical system, an engineered system that replicated the dynamics that you cared to think about. So in fact, this is in the early days of economics, when people were starting to build mathematical models of economics before digital computers were commonly available. And in fact, what economists did, or some economists did, was to build fluid mechanical systems, that is, pipes and chambers and pumps representing parts of an economy. So that they were trying to build simulators out of water that was simulating the processes that they believed occurred in a real economy, and that's an approach that's been profitable in different branches of science. How do you solve the mathematical problems of whichever discipline you're in using a simulator that is a physical apparatus that to your knowledge replicates the behavior of the thing that you're trying to study? And so that's one of the other areas that we're interested in is engineering novel systems in very specialized hardware that are capable of solving problems in a sense that's not the same as what a digital computer is doing. They're in a sense replicating the dynamics and the behavior of the thing that we're interested in, using an engineered system. So an example of that would be a long-standing question in theoretical physics and in applied physics, which is about high temperature superconductivity. So that's a phenomenon that's been known about for 30 years. Nobel Prizes have been awarded for the discovery of it.
So just to clarify for people, high temperature in the common sense in this language still means cold, just not as
That's
cold.
right. Yeah. So it took many decades. Well, when superconductivity was first discovered, when people were messing around with liquid helium, and high temperature really referred to the ability to observe superconductivity above liquid nitrogen. So it is still indeed very cold. Liquid nitrogen happens to be much cheaper than liquid helium. So if you could, if people are interested in it for all sorts of reasons, but the hope or the promise, as it was 20 or 30 years ago, was that maybe we build all our power cables out of very high temperature superconductivity, that is at room temperature or ambient temperature, so that we can carry electricity around the country or around the world, even with zero losses. So that was a sort of a pie in the sky dream. The thing is, we still don't actually understand the mechanism for high temperature superconductivity, and it's believed that quantum fluctuations are really important in understanding that phenomena. And so people have a belief that various models in quantum mechanics, theoretical models in quantum mechanics, have built into them the mechanism of high temperature superconductivity. It's just that nobody's been able to demonstrate that in a convincing way. So there's statements of belief about where the physics of high temperature superconductivity comes from, but we just don't know that those claims are true or not. Now, the problem there is that we can't simulate those quantum mechanical models on a digital computer with enough accuracy in a reasonable amount of time. And so one approach to that problem would be to say, let's build in a real physical system that's completely different from the physical ingredients that are in real high temperature superconductors. Let's build in this engineered system the kinds of microscopic details that we think live in this theoretical model called the Hubbard Model. And so for example, you spoke to Mike Bierchuk, who builds ion traps. And so you can imagine taking a string of ions in an ion trap, or a 2D array of ions in an ion trap, and simulating this so-called Hubbard model. That's the model that people believe contains high temperature superconductivity, simulating that in the ions of the ion trap, and measuring then properties of that physical system, and discovering whether or not that has the correct behavior to understand high temperature superconductivity. Or perhaps out of superconductor, I mean, this is sort of slightly ironic, using low temperature superconductors, niobium or aluminium, in the kinds of experiments that people build for digital quantum computers, using the same sorts of underlying hardware to simulate a Hubbard model that would then, in the same way, perhaps let you understand whether high temperature superconductivity emerges from this particular model. So that's a little bit ironic, because you're using low temperature superconductivity to simulate a model which you hope explains high temperature superconductivity.
I mean, bootstrapping is not a big problem.
No, that's right. But so the point there is that you've really got you've fabricated an entirely synthetic system that has nothing to do with the problem that you're trying to solve, except that you believe that it replicates the model that you hope contains the physics that you're interested in. And just like, the analogy with economics, building a fluid mechanical system with pumps and pipes and reservoirs has nothing to do with the real economy, except that the people who are doing it believed that the mathematics underpinned the two systems, the economic system and the fluid mechanical system, were somehow related to one another. So that's one of the other aspects that of quantum mechanics that we're interested in our centre, is how you simulate exotic systems in very, very well controlled, engineered devices.
So, I mean, there's an interesting sort of economical question on this kind of thing when you're simulating specific systems rather than, say, a full digital machine. Sort of return on investment is sort of, these systems are hard to build. These things cost a lot of money to build. I mean, in the context of high temperature superconductivity, I can imagine that there is a potential return on investment if you could build something that tells us, how the high temperature superconductors work. But how do you see this fitting in sort of with other such problems? Are they very practically related? Do they have a good motivation for building these things, or a lot of them just sort of esoteric scientific problems that, you know, help us understand things but don't have any immediate application?
Well, I mean, I'd say a lot of people in the field are interested in it for really just for curiosity. I mean, that's what drives academics. But you know, the history of science is that curiosity-driven research often does lead to really big economic impacts. But having said that, I mean, just that example of high-temperature superconductivity, if we were able to deploy quantum mechanics in the service of understanding that problem in the way that I described, building simulators, then that by itself is a big. There's potentially massive payoffs in electricity distribution, power distribution, and also in transportation. So building levitating trains using high-temperature superconductors would revolutionize transport. Now, the payoff in those cases would be measured in the billions or tens or hundreds of billions of dollars, and the investment required is measured in the tens or hundreds of millions of dollars. So, you know, the return on investment, if it works, is absolutely phenomenal, right? So it only has to, that kind of a venture only has to work one every 100 or 1,000 times that you've made your money back. Now, in fact, we also know of other systems where a simulator would be very valuable, not just high-temperature superconductivity, but developing new drugs, new chemicals for all sorts of different applications is a really hard problem. And at the moment, the standard approach is really to manufacture new compounds, whether you get them from the Amazon rainforest or out of a lab, to synthesize and purify various compounds that you believe might have some advantage in curing this or that disease, or synthesizing new catalysts for this or that industrial process. But it's very much a case of going out and looking for needles in haystacks. And we don't really have we've got lots of rules of thumb, and chemists for the last 200 or 300 years have figured out how to understand chemistry in a way that does help them to make progress. But there's no rational way of really understanding the quantum mechanics that's at the heart of every single molecule in a completely rational and controlled way. So if you had a quantum simulator, the hope would also be that you could simulate, for example, chemical processes. So maybe we can design new catalysts that help us to make fertilizers more efficiently. Perhaps we can simulate compounds that we believe might help to solve different diseases that we care about. So
this is a distinction that I think some people still find a little bit confusing when we talk about things like drug synthesis and drug manufacturing. Are you saying that a quantum computer can help us? You know, say we have a problem, whether it's a catalytic problem or a medical problem, does quantum simulation allow us to figure out what kind of molecule we would need to synthesize to do it? Or does it allow us to sort of, you know, what comes first? Do we start with the molecule and then simulate it? Or do we start with the problem and then find the molecule?
I'm not a chemist, so, you know, I don't want to speak too much about what those guys do at the moment. But my understanding is that really they find molecules and then they see if they work on a specific problem. So, but in the end, a molecule is just an atomic scale machine. So the world of nanotechnology already exists, and it's existed for hundreds of years because chemists are synthesizing nanometer scale atomic machines. That's just another name for molecules. And so the question is, you know, in conventional engineering, mechanical engineering, let's say you've got a problem which is I want to get from here to there. Well, there's lots of ways to solve that. You could hop on a horse, you could walk, or you could invent a bicycle or a car. And, you know, the latter two solutions are statements about a machine that helps you to solve a particular problem. But, you know, you have to first identify the nature of the problem. So I guess in drug design, you have to identify chemical pathways, biochemical pathways that are relevant to the specific disease that you're concerned with, and then come up with potential interventions, molecular interventions that will rectify whatever that problem is. And so it's then the question is, are there molecules, are there atomic machines that will do the task that's required to disrupt that biochemical pathway, the pathological pathway that you care about. And so at that point, you could test a whole range of different compounds in the lab, which is what people do now, to see whether they do correctly intervene in the process that you're interested in.
Mm-hmm.
But another way would be to do what engineers do, which is to have an idea, think of an engine or an aeroplane or whatever, and then use computers, use rational design principles to design that machine to function in the way that you want it to. And so that would be, I imagine, the way these things would be deployed, is that you still need the biochemists to understand the complicated pathways that are involved in whatever the problem is, whether it's catalyst design or whether it's medical drug design. But then at some point, one would like to go away from wet bench tests of hundreds or thousands or millions of compounds and ask a computer, whether it's a digital computer or an analog quantum computer, to help you with that process. So it would be it would fit into the workflow of that community in a way that helps them to design and rationally select compounds more effectively.
Great. So, I mean, now, we sort of talk a bit more broadly as to sort of what the field is, but why don't we go now into some sort of more specific highlights about what you do? You come from the theoretical side. So, I mean, I know you have a lot of projects. I mean, if you had to pick one or two to sort of say, well, these are the exciting ones and these are the ones that I want to point out, what would they be?
Yeah, okay. Well, as you said, I work on a lot of things. Well, I'll tell you something that I've worked on very recently, but that's been part of my career since I started my PhD 15 years ago, which has been thinking about quantum dots. So quantum dots are microscopic objects, sort of a micron across or smaller, which they behave like artificial atoms. So an atom is a point-like object in space, and it has the quantum mechanics of atoms is relatively well understood. And they're certainly characterized in one sense by having a very well understood energy level structure. That is, atoms in everyday life have got a spectrum that's associated with the transitions between the states of the atom. So if you think of sodium lamps, which are a bright yellow, that's because there's a very strong yellow color transition. And quantum dots are a bit like that. They're artificial atoms. They're engineered systems. They're much bigger than real atoms. And they're built on top of, out of semiconductors. So you take a lump of semiconductor like silicon or gallium arsenide and make it very pure, and then with a variety of tricks, you build structures on that semiconductor wafer that are at the scale of microns or smaller, and those tiny structures are also sort of point-like. They're not extended in all three dimensions. They're actually localized in all three dimensions. And so that object, that microscopic object, has the same sort of behavior as real atoms in that it's got a well-defined set of energy levels. Mm-hmm. And so so then now you've got a whole toolbox that lets you engineer effectively atoms with all sorts of properties that you might be interested in. Now, it's sort of amazing. It really surprised me when I learned about this years ago, is that those artificial atoms, even though they're inside what would often be considered to be incredibly dirty and complicated semiconductor crystal structures, they still behave very much like atoms. So the quantum mechanics inside quantum dots is the same quantum mechanics that makes atoms do their thing. And it's a very strong effect. You can't understand quantum dots without understanding quantum mechanics, even though they're, in a sense, the dirtiest sort of system that you can hope to imagine in experimental. So solid state physics is the study of solids, and there was a community of people who used to call it squalid state physics, because the complexities of the structures and crystal lattice and impurities were enough to make it a very difficult problem to solve. But nevertheless, people have built these things, and so I'm very interested in what you can do with those. And so some people I've worked with for a number of years in the United States have recently demonstrated some really nice results in that system. So taking quantum dots coupled to microwave resonators, which are basically just like guitar string in a sense. There is they have resonant frequencies that the quantum dot frequencies can interact with, and they see all sorts of interesting things like gain and population inversion, and the kinds of things that people have observed in atoms for many decades are now starting to be observed in these quantum dot systems. So understanding how those things work, in spite of and because of their interaction with their environment, the environment of the crystal lattice and the impurities in the lattice and so on, is, I think, a fascinating problem just scientifically. And there's hope, as we said before, there's hope that there might be some applications of that, for example, with new microwave sources and so on.
So what's the motivation? You say these quantum dots act as basically artificial atoms, but they're also noisy, and the systems are unclean and impure. So why would you build such a thing when we already have atoms?
Well, atoms are given to us by the universe. There's not much we can do with them, and so on the one hand, atoms are almost the Platonic ideal. Every single calcium atom is the same as every other calcium atom, except for the fact that they might not have desirable frequencies, that transition frequencies. They might be very hard to trap. I mean, atoms, it's taken many decades for people to learn how to manipulate single atoms and hold on to them, let alone do anything sophisticated with the internal structure of the atom. So atoms are great, and they have their own set of problems. But if you think about the digital computer revolution that we've enjoyed over also many decades, that's relied on the fact that we've been able to make nonlinear electronic devices like transistors in silicon and in other semiconductors as well. So there's a huge infrastructure in place for building outrageously useful devices in semiconductor materials. And so if you can take advantage of that fact and all that huge amount of investment and expertise that people have developed in semiconductor technology, there's, I think, great hope that you can do something useful in the quantum space. So maybe you can build quantum computers out of quantum dots. That's been a long-standing proposal. Maybe you can use them for quantum simulators, but also maybe you can use them for these sort of micro maser, single artificial atom maser systems. And I don't know. I'm not sure where it's going to go, but I think they're great. And
I think that's the whole idea with fundamental research, is you're not too sure, but it sounds exciting.
I think so. Yeah. But in short, the answer is that you can engineer them. You can build them to spec, so to speak. Whereas atoms, we've got about 112 different types of atoms that we know about, and a few isotopes of each of them. But that's it. There's no more atoms that we can find.
Or at least ones that are highly radioactive.
Indeed.
So, I mean, in Australia, we've basically got the two main centres. We've got EQuS, which is who you work for, and we've got the Centre for Quantum Computing and Communications Technology. You both fundamentally work on quantum mechanics, and you both fundamentally work on quantum technology. But your mandates are somewhat different. Obviously, with CQ-C2T, they're focused very much on quantum commuting and communications. But in terms of sort of cross-collaborations and sort of, where the technologies meet in the middle, how does that work? I mean, is there much crossover between the two systems and between the two centres and the two sets of technologies that are being worked on?
Certainly. So people in both, there are people who are in both centres, and there are people who share different research grants with across the centres. So on the ground, there is plenty of collaboration between different people in each of the centres. Again, I mean, I guess the distinction between the two, saying that we both work on quantum mechanics is a bit like saying that there's two different research groups who do mechanical engineering or something. Quantum mechanics is an incredibly broad area, and there's certainly room for a great many people working on it. The UK over the last few years has been ramping up spending in quantum technologies. And I don't know if you saw China's planning to or have just deployed a satellite, a quantum communication satellite. So
I saw that.
There's a lot of interest in the space, and so I think this is one of the great things about Australian science. In fact, is that though compared to the big centres in Europe and North America and Asia, I think in this particular space we've invested from the start. We've had some of the earliest results in quantum information and quantum technologies really did come out of Australia, and that was part of a very close-knit international community. And so I think Australia is well positioned to exploit our historical legacy that a few people began here in the 80s and 90s. And again, our focus is different. So quantum computing is it's a very specific objective there, and objective. When in our centre, the Engineered Quantum Systems Centre, I guess the objectives are more diffuse, but nevertheless, I guess we still see that there's lots and lots of avenues that haven't been pursued that we all need to explore. And I think that having both centres is for the better. It makes the research environment here richer, and there is a lot of overlap, and so lots of collaborations going on the ground between professors in both centres, all the way down to between PhD students in each of the centres.
So I mean, this rolls on nicely to sort of the last third of a discussion that I usually do on these podcasts is sort of where the field is and where you see the field going. Now, you've been involved in quantum technology and quantum computing now for longer than I have. So you've seen how this has evolved from sort of the late 90s, early 2000s, all the way through till now. Certainly when it comes to the investment from the quantum hubs in the UK, whether it's this earmarked €1 billion investment from the European Union, the Chinese satellite, Google, IBM. Give us a bit of a run through sort of your opinion as to sort of how this evolved from really what seemed to be a very purely academic endeavour to now something that has really started to explode into the private sector, and certainly quantum computing. You don't have to wait too many days before you see some new headline in the paper about what quantum technology is doing worldwide.
Yeah, I guess there's lots of answers to that question, but like in any area of technological area that turns into a big industry, really that there had to be a killer app, so to speak. There had to be a killer reason for why that academic discipline turned into something bigger. So if you look back in history, engines, which were invented in the Industrial Revolution, they were the heart of the Industrial Revolution. They started off as things that backyard scientists were tinkering with, or aristocratic scientists probably were tinkering with, and of course they proved to be incredibly useful. They also were the basis for what are quite esoteric areas of physics like thermodynamics and statistical mechanics. So that industry took off because there were huge applications of the engine, and we don't need to go into those because it's self-evident just looking around us where internal combustion engines have taken our society. Things like the laser, it was when it was invented as an idea, the applications were relatively unknown, and I'm trying to remember what I can't remember now, but there's the business model that people started thinking about for why you might need lasers was incredibly limited, and so but now lasers are ubiquitous. So what you need really is one key area where you think that device or that idea is going to play a role. Digital computers, the applications for them were in the military, calculating ballistic trajectories and breaking codes. So the reason that those technologies took off was largely because of very specific applications that people identified that the idea would be useful for. And so in the case of quantum technologies, I guess it's what I've already described. So LIGO, the laser interferometer that discovered gravity waves, in a sense, kicked off a lot of the thinking about quantum metrology in the 1980s, and so that was probably one of the first places that people started to appreciate that you could exploit quantum mechanics to make measurements better. And then over the next few years, after the initial papers on quantum metrology came out, people were thinking along the lines of whether you can generalize computation, and so can you build a quantum computer? And it was, I guess, in the mid-90s when there were a few specific algorithms that were proposed, Shor's algorithm most famously, in which it was demonstrably the case that a quantum computer would outperform the best known classical computer at solving a specific problem, in that case, factoring. And it turns out factoring, as I'm sure you've discussed on your podcast, factoring is a key application in a very specific area of industry, and in particular, it's important for internet encryption. So, so there's a group of people that perhaps want to break internet encryption, and those people have quite a lot of money to spend, and so that, in a sense, I think drove historically the desire by some segment of industry to have a quantum computer. Now, I think people in industry can see that there is at least one application, or there are a few applications where a quantum computer will be useful, and just on the basis of historical sort of comparisons, as I sort of described before, once a thing starts taking off, all sorts of clever people start thinking about it in different ways and come up with different different uses for it. So the laser is now used in well, probably less so now, but for a long time it was used in CD players and DVD players, although they're probably going out of fashion a bit. But laser technologies in 3D point cloud mapping for autonomous vehicles are going to be a huge market, and so on. So the point is that a thing like a laser, which started off with a very limited set of tasks that people thought it would be good at, is now ubiquitous. And I think that's where quantum computing is, and quantum technologies broadly. There are known areas where they'll be useful, and we just need to build them now. And it's a good guess that clever people will come up with new things to do with them that we haven't even thought of yet.
Yeah, I think that the general consensus of people I've been speaking to has been, look, get the technology in the hands of people that, frankly, are smarter than us, and they'll come up with a whole bunch of things.
Yeah, I mean, I guess that's where one should be a student of history, and it's not so much people being smarter. It's just that at the moment the problems we have to solve to build a quantum computer are so overwhelming, in a sense, that smart people who are interested in it should be thinking about those problems. That's what we need to do now. Once we've solved those problems, which we will, then those same smart people, or their intellectual descendants, can put their thinking caps on and start trying to broaden the scope of what the technology is capable of doing. And I'm confident just on the basis of history, without necessarily having any evidence in favour of that.
No, I think the historical lesson is a good motivation to believe that this is going to happen again.
I guess there is a fundamental physics question as well, which I think is just as powerful for physicists, at least, which is that quantum computers in particular, but more broadly engineered quantum systems, in a sense, represent an entirely new state of matter that to our knowledge hasn't existed in the universe before. That is like a system that can be made arbitrarily big and still retain all of the quantum mechanical coherence that is at the heart of, say, atoms. So that's the thing that doesn't exist in the universe now that we know of, and doing that is really answering it's the Mount Everest question. Why try? Well, because we can, because it's there and because we can. So I think there's a sort of cultural reason to think that building an entirely new kind of material that is a quantum computer is it's worth doing for its own reasons.
Yeah, no, I completely agree. Now, there was one thing I wanted to bring up, and we can choose to discuss it or not. It's up to you. You sort of alluded to it a few minutes ago when you were talking about autonomous vehicles. Now, correct me if I'm wrong, you wrote an article for, was it Forbes?
I was the Australian Financial Review.
For Australian Financial Review about because this seems to be a little bit of a pet project or a pet hobby of yours, something you're certainly interested in. Did you want to talk about sort of your perspectives on this at all?
Sure, very briefly. I mean, I have a few sideline projects, and that's one of the great things about being a scientist is that one can follow one's nose, and so I'm pretty convinced that, and I'm not Robinson Crusoe here, that autonomous vehicles are going to change the way cities work for the better, and so I have some interest in that, and I guess I've got a research involvement, which is in LiDAR, developing new techniques for imaging with laser ranging and velocimetry, and so that's something that I've got going on right now, and quite excited about it. There's some big players in the field, so it's a bit daunting, but yeah, maybe we can come up with something good.
Well, hopefully. So, I mean, we're getting close now to sort of the 45-minute cutoff that I usually do these things for. So we'll go with the standard last question that I ask people is if I try to pin you to a prediction with these systems, whether it's quantum computing or just the more broader idea of an engineered quantum system, I mean, what would you think is a reasonable prediction of what could be around in 5 or 10 years in terms of what the general public would see?
What will the general public see in 5 or 10 years? I suspect, well, so I thought you were going to ask the question of when will we see, say, a quantum computer, which a lot of people ask. And the short answer to that question is we've already got them, so they exist already. So when will we see them? Well, we've already seen them. And then they say, oh, yeah, but I mean something useful. And so that's more along the lines of your question is when will we, not when will we see something useful, you're asking what will be useful around in 5 or 10 years. And really, I just don't know the answer to that question. I suspect that we'll have quantum computers that are capable of doing things that classical computers can't do now, albeit that problem is simulating a quantum computer. So that's not necessarily a useful thing. It's just a demonstration of a device which goes beyond classical capabilities. I suspect that we'll have deployed quantum cryptography networks. I mean, there are a few that exist now in sort of demo in a demonstration setting, but I suspect that there'll be some areas where there are deployed quantum communication protocols for real purposes, so maybe interbank communications or intergovernmental communications. And we might just start seeing the first quantum simulators being built. In terms of things like quantum metrology, we already have measurements now. So one of my colleagues here at UQ, Warwick Bowen, has measurements using squeezed light, where he sees in a biophysics experiment, he's looking at a small intracellular bit of stuff. So he looks at cells, and they've got organelles and so on, and so you can look at how a particle within a cell, a living cell, behaves. And he uses squeezed light, which is the sort of light that people are talking about putting into LIGO, the interferometer, to measure the motion of particles within a single cell with lower noise than you can do otherwise. And the point there is that with lower noise, you can measure things on shorter timescales. So they're already seeing phenomena in biological systems that the claim would be that you can't observe without that technology. So that's been demonstrated in a research paper, and so one can imagine that will be deployed more widely. That is quantum assisted biological measurements, where you use the properties of quantum light to measure to measure properties of biological systems with lower noise and with higher bandwidth.
Okay, so I think we've got a bit of a rock solid prediction there. There's something related to biosensing might be around the corner.
Indeed, yeah.
Okay, so we'll close this off. Generally, I like for everyone who comes on, if there's anything interesting happening at EQuS or EQ or anything you want to plug that's coming up shortly.
Well, so we're all on tenterhooks because we're waiting for the outcome of the second of the refunding round. So we've asked, so EQuS will run out at the end of next year, and we shortly will find out whether we have been extended or not. And so I think, well, it's very exciting. There's never been a more exciting time to be a quantum physicist in Australia. And we'll you might hear cheers, or you might hear people crying from this part of the world in literally a few days or a week. Anything else to plug? No, but people are coming to visit. Come by, and Australia's a long way from everywhere, and so whenever people are in the country, we encourage them to come by the nodes of our centre and visit and see what we're up to, and let us know what they're up to. So open invitation for people to come and check us out.
Well, I think that's a good note to leave on. So as with usual things, I'll put all the links to Tom's webpage and Twitter accounts and all the kind of things you would need if you want to get in contact with him or anyone else from EQ or EQuS. But no, I think it's a good note to leave on. And Tom, thanks a lot for giving me an hour of your time. Thanks, Simon. It's great talking. Cheers. So thanks again, everyone, for joining in today. This will obviously be uploaded to iTunes and SoundCloud very, very shortly. We'd like to say that we're now on Google Play's podcast network as well as iTunes. So the link is in our Twitter feed, and obviously just search up for meQuanics on Google Play, and you should be able to download us there too. So our next episode should hopefully be sometime in the next week or so, possibly either with Andrea Morello from the University of New South Wales in Sydney, or Andrew Cross from IBM Research in the US. Who comes first, we're not sure yet. We have to confirm some times. But again, check out our YouTube channel and all our social media accounts for any updates. So thanks again. Cheers, everyone.